In the quiet, pre-dawn hours of March 3, 2025, an amateur astronomer in New Zealand peered through his telescope at what should have been a familiar corner of our cosmic neighborhood. What he saw instead was completely unexpected. A brilliant, new point of light blazing where none had been just days before. What he'd stumbled upon wasn't just any celestial event, but rather one of the most spectacular cosmic phenomena we can witness from Earth. A supernova explosion. In the days that followed, this dazzling stellar detonation would not only capture the attention of the global astronomical community, but would reveal secrets about stellar evolution that have profound implications for our understanding of the universe and our place in it. A supernova isn't just a star dying. It's a star going out in the most dramatic fashion imaginable. In the case of our newly discovered friend, designated SN 2025A, we're witnessing the spectacular death of a white dwarf star that accumulated too much mass and crossed a cosmic threshold that triggered an unstoppable thermonuclear explosion. This isn't just a burst of light. It's the violent release of energy equivalent to 1028 megatons of TNT, briefly outshining entire galaxies and enriching the cosmos with heavy elements that will one day form new stars, planets, and perhaps even life. I'm Alex, and you're watching Space Truths. In today's video, we'll explore this extraordinary new supernova, how it was discovered, what makes it special, what scientists have already learned from it, and what you might be able to see with your own eyes if you know where to look. From the explosive physics to the cosmic implications, we're diving deep into one of the most energetic events our universe has to offer. It seems like a cosmic irony that with all our advanced space telescopes and monitoring systems, it was a hobbyist astronomer with a 10-inch telescope who first spotted this extraordinary event. But that's exactly what happened when Gerald Thompson, a retired physics teacher from Auckland, was conducting his routine observing session of nearby galaxies. Thompson immediately recognized the significance of his discovery in the spiral galaxy NGC 4424, located about 54 million light-years away in the constellation Virgo. Within hours, his observation was confirmed by other amateur astronomers across the Pacific, and within 24 hours, the world's most powerful telescopes had swiveled to focus on this cosmic explosion. This isn't just any supernova, though. SN 2025A belongs to a special category called Type Ia supernovae, cosmic explosions that occur with such consistent brightness that astronomers call them standard candles. These stellar explosions have played a crucial role in one of astronomy's most important discoveries, the accelerating expansion of our universe. When I realized we were looking at a Type Ia supernova that was still in its earliest stages of explosion, I knew this was going to be a game-changer, said Dr. Elena Ramirez of the Keck Observatory. We rarely catch these events so early in their development. Let's take a step back and understand what's actually happening when a supernova like this erupts. Type Ia supernovae occur in binary star systems where at least one star is a white dwarf, the dense Earth-sized remnant of a sun-like star that has shed its outer layers. These white dwarfs have an interesting property. They can only support a specific maximum mass, about 1.4 times the mass of our Sun, called the Chandrasekhar limit. When a white dwarf steals material from its companion star and approaches this limit, something extraordinary happens. Picture the white dwarf as an increasingly pressurized cosmic time bomb. As material from its companion accumulates on its surface, the white dwarf's core becomes denser and hotter. Unlike a normal star that would expand to relieve this pressure, a white dwarf is held together by quantum forces that prevent its particles from being squeezed any closer together. But there's a tipping point. When the temperature reaches about 10 billion degrees, carbon atoms in the star's core begin to fuse uncontrollably. Within seconds, a runaway thermonuclear reaction consumes the entire star, releasing an almost unfathomable amount of energy. The star doesn't just die, it's obliterated, hurling its material outward at speeds of up to 10,000 kilometers per second. The light we're seeing from SN 2025A began its journey to Earth 54 million years ago, when mammals were just beginning to diversify after the extinction of the dinosaurs. Think about that for a moment. The explosion we're witnessing now actually occurred when the ancestors of humans were small, shrew-like creatures scurrying beneath the feet of early mammals. The light from that explosion has been traveling through the void of space, crossing millions of light years, only to finally be captured by Gerald Thomson's telescope in his backyard in New Zealand. What makes SN 2025A particularly exciting to astronomers is not just that we caught it early, but that it's unusually close by cosmic standards. At just 54 million light-years away, it's one of the nearest Type Ia supernovae observed in the last decade. This proximity means we can study it in extraordinary detail across the electromagnetic spectrum. Already, telescopes around the world and in space have been collecting data that's giving us unprecedented insights into the physics of these explosions. The James Webb Space Telescope quickly pivoted to observe SN 2025A in infrared wavelengths, while the Chandra X-ray Observatory captured the high-energy emissions from the explosion. Ground-based observatories like the Very Large Telescope in Chile have been tracking its spectral evolution night by night. Having so many instruments focused on a single event this close gives us a multidimensional view of the explosion process, explains Dr. Hiroshi Tanaka of the National Astronomical Observatory of Japan. We're seeing details in the early expansion and nucleosynthesis that have never been observed before. One of the most fascinating aspects of this supernova is what we're learning about the production of heavy elements. You see, the calcium in your bones, the iron in your blood, and the gold in your jewelry were all forged in the hearts of dying stars. Type Ia supernovae are particularly efficient factories for producing iron and similar elements. The spectral signatures from SN 2025A are already revealing exactly how these elements form and in what quantities. Early analysis suggests this particular explosion produced enough iron to form about 600 Earth-sized planets, made entirely of the metal. But what about the star system itself? What was it like before the explosion? This is where things get really interesting. By analyzing pre-explosion images from the Hubble Space Telescope's archives, astronomers have identified what they believe was the binary system that produced SN 2025A. The data suggests the white dwarf was orbiting a red giant star, gradually siphoning material from its bloated companion. Computer models indicate the two stars were locked in an incredibly tight orbit, completing a full revolution around each other in less than 4 hours. It's like they were performing a cosmic death spiral, says Dr. Ramirez. With each orbit, the white dwarf pulled more material from its companion, sealing its own fate. Now, I know what many of you are wondering. Can you see this supernova yourself? The answer is yes, but you'll need some equipment. SN 2025A has brightened to about magnitude 11.7, which means it's invisible to the naked eye but easily within reach of a modest amateur telescope or even powerful binoculars. It appears as a bright bluish-white point of light near the edge of NGC 4424. If you live in the northern hemisphere, the galaxy is visible in the evening sky in the constellation Virgo, not far from the bright star Spica. For those in the southern hemisphere, you'll need to wait until the early morning hours to catch it. Dozens of astronomy apps can help pinpoint its exact location, and I've included links to finder charts in the description below. The supernova is expected to remain visible through telescopes for several months, gradually fading as the explosion's energy dissipates. If you do have a chance to observe it, take a moment to appreciate what you're seeing. The catastrophic end of a star system that once might have harbored planets, and possibly even life, now illuminating the cosmos with its final, spectacular show. While supernovae are relatively common in the universe, with about one occurring every second somewhere in the observable cosmos, catching one this close, this early, and of this particular type is an extraordinarily rare opportunity. The last comparable event was SN 2011 in the Pinwheel Galaxy, which astronomers still refer to as the supernova of a generation. SN 2025A may well surpass it in terms of scientific importance because of our improved instruments and earlier detection. Let's talk about what this means for our understanding of the cosmos more broadly. Type Ia supernova are crucial to cosmology because of their consistent peak brightness. This property allows astronomers to use them as cosmic yardsticks to measure vast distances across the universe. It was through observations of distant type, Ia supernovae in the 1990s, that scientists discovered the universe's expansion is accelerating, a shocking finding that led to the concept of dark energy and earned the 2011 Nobel Prize in Physics. SN 2025A offers an unprecedented opportunity to calibrate these cosmic yardsticks with greater precision than ever before. By understanding exactly how the explosion unfolds in a nearby supernova, where we can observe every detail, astronomers can better interpret observations of similar explosions billions of light-years away. This improved calibration could help resolve some nagging discrepancies in how we measure the universe's expansion rate, a problem known as the Hubble tension that currently represents one of cosmology's biggest puzzles. Beyond cosmology, this supernova is teaching us about the final phases of stellar evolution. Every star that resembles our Sun will eventually become a white dwarf. While most white dwarfs simply cool down over trillions of years, those in binary systems might face a more explosive fate. By studying SN 2025A, we're essentially getting a preview of what could happen to many star systems throughout our galaxy, including potentially our own in the very distant future, though our Sun will likely die a much quieter death. Of course, supernovae aren't just destructive forces, they're also creative ones. The heavy elements forged in these explosions are essential building blocks for rocky planets like Earth. The shock waves from supernovae can also trigger the collapse of nearby gas clouds, potentially initiating the birth of new stars and planetary systems. In this cosmic cycle of death and rebirth, supernovae play a vital role in driving the chemical evolution of galaxies. SN 2025A is providing a front-row seat to this fundamental process. There's another aspect of this discovery that I find particularly poignant. In an era of automated sky surveys and AI-powered detection algorithms, it was human curiosity and dedication that first spotted this cosmic wonder. Gerald Thompson, the amateur astronomer who discovered the supernova, had been systematically observing nearby galaxies for over 20 years, comparing each night's view with previous observations. I almost skipped over NGC 4424 that night because clouds were moving in, Thompson recalled in an interview. But something told me to take just one more look. That decision led to one of the most important astronomical discoveries of the decade. This speaks to something fundamental about our relationship with the cosmos. For all our advanced technology, there remains an irreplaceable value in simply looking up with wonder and attention. The universe reveals its secrets not just to our most sophisticated instruments, but to those who observe with persistence and care. As we continue to monitor SN 2025A in the coming months, each new observation will add another piece to our understanding of stellar explosions, Already, unexpected findings are challenging existing models. For instance, the explosion appears to be expanding asymmetrically, suggesting the white dwarf may have been rotating unusually rapidly before it exploded. There are also hints of unusual chemical signatures that don't quite match theoretical predictions. These puzzles remind us that despite centuries of astronomical progress, the universe still has plenty of surprises in store. Each anomaly and unexpected observation pushes us to refine our theories and develop new models that better capture the complexity of cosmic phenomena. So, what's next for SN 2025A research? In the coming weeks, astronomers will be watching closely. As the supernova reaches its peak brightness, they'll track how different chemical elements appear in the expanding debris, map the structure of the explosion, and search for any traces of the companion star that may have survived the blast. Further out, years from now, they'll observe how the ejected material interacts with the surrounding interstellar medium, potentially forming a supernova remnant that could be studied for centuries. For now, though, we can simply appreciate the cosmic serendipity that brought this distant explosion to our attention at just the right moment. In the vastness of space and time, our brief window of observation represents an almost infinitesimal instant. Yet in that instant, we're privileged to witness and comprehend one of the universe's most profound processes, the violent end of one stellar story and the distribution of ingredients for countless new ones. Thanks for watching. If you enjoyed this exploration of SN 2025A, please consider supporting Astrom on Patreon. Your contributions make it possible for us to continue bringing you the latest and most fascinating developments in astronomy and space science. Don't forget to subscribe for more cosmic content, and check out our playlist on stellar evolution for a deeper dive into the life cycles of stars. Until next time, keep looking up. You never know what cosmic wonders await your discovery.